the general statements or the general conclusions we made when we were in sections 11.1 and 11.2, and when we did the notes from that. We talked about the fact that whenever something is rolling, it has both rotational kinetic energy and it has linear kinetic energy. And that's what you're seeing on the left-hand side of the screen over here. And then at the end, as we went through the class, if you recall, we came up with a couple of different things. First, we looked at the concept of rolling down a ramp, and we said that we can come up with some generic solutions for this, and those two solutions are down here at the bottom. Okay, the static friction force, and then the actual acceleration of the center of mass of this object here. So we're going to utilize this information in these next coming examples. So I tried to summarize them all on this first slide here. Let me go to the second slide now, so we can take a look at an example. Now these examples are questions out of the end of the chapter in your text, so I could let you know which one each of them are as we get to them. But I'd rather you obviously not look ahead to see what the answer actually is, so I'll put up those numbers in a moment. So the first one we're going to look at is example 3, and it says a 140 kilogram hoop rolls along a horizontal floor so that the hoop's center of mass has a speed of 0.15 meters per second. How much work must be done in order to stop the hoop from rolling? Okay, so right off the bat for this kind of a problem, we have to start thinking about the kind of solution we're going to look at. As soon as it says something like how much work must be done, and we're thinking about things that are rolling, when we think about work done, what can we use when it comes to work to compare it to something that is rolling, that has motion? How is work related to something that's rolling and eventually comes to stop? What would be the, what do you got? Distance will help for sure. More than that though? Yeah, energy, Chris, very good. The kinetic energy we're talking about here. So if you remember that we know that the work done is equal to the change in kinetic energy, this law applies in all cases, but now the change in kinetic energy is not just linear, but it's also rotational. So we have to ask ourselves, when it stops, well, what does that mean? So let's see, the work done is final kinetic minus initial, and because it's stopping, the final kinetic energy is going to be 0 in this problem. So really, when we look at this example, when we're trying to figure out the work done, it's going to equal negative K0, which is really the initial kinetic energy of this hoop. Now, let's figure out what that initial kinetic energy is. Well, we've got, again, the kinetic energy for the rotating piece, which is 1/2 I omega squared, and the kinetic energy for the translational piece. The issue, though, obviously, is what? What's the issue here? What's the concern? Good. We don't have a radius in this problem. Right off the bat, if we're going to do this, it's like, oh, well, what's the radius equal to? And where do we see radius? Well, I don't see radius anywhere here, but it's embedded in other variables. What variables is radius embedded in this last line? Good. I. Good, Chip. And what else? It's hidden, though. It's not obvious. Good. Omega. Yeah, omega, remember, we know that we have V equals R omega, or V equals omega R. So if we want to replace omega, which we probably do because we have nothing about omega in this problem, let's write it as V over R. So in the next line, the work done equals 1/2. We'll put the I value in a moment. Omega is going to be, again, V over R. Now, what's the I value in this problem? What's the I value going to be in this problem? Yeah, it's a hoop. Very good. Chris, you got the table up in front of you? I see a hand up there. Say again? Not the hoop. The hoop is not 1/2 mr squared. I think that's the disk I think you're thinking of. Yeah, the hoop is the one that's just mr squared, actually. Okay, it's one of the few that's does not have a coefficient in front of it. I think it's actually the only shape on our list that doesn't have some beta value. Remember we've been talking about beta as in like the coefficient in front of mr squared? It doesn't have a value there, it's 1. And the rationale, think about it logically. All of the mass is concentrated on the very edge of the hoop. That's why there's no fraction there. So in this problem, the I value is just mr squared. So as we noticed here, Chris pointed out before that r is not given. Well, now we can see why r is not given, right? Let's write this out. This is going to be equal to negative, and this is going to be a 1/2. Then we're going to have mr squared times v squared over r squared. Those r squareds are going to cancel. And then plus the 1/2 mv squared. So it turns out, interestingly enough, that r drops off, and we have 1/2 mv squared plus 1/2 mv squared. Right? Again, look at the equation and what's left over, right? This is just 1/2 mv squared, and then 1/2 mv squared. So as a result, what we're going to notice here is that our work done is just going to equal to be negative mv squared. Okay, and mass is given, and so is the v, the velocity of the center of mass. So we can get a number. Okay, and that'll give us our work done. I have a value written down for us already. Negative 3.15. Negative 3. Oh, wait, is this in 140 kilograms? Sorry, it's not 0.140, it's 140 kilos. I thought it was written as grams at the top there. Okay. Negative 3.15 joules. So a problem involving rolling, where we notice there's no elevation change, right? No elevation change. So what type of energy was not involved in this problem at all? Yeah, no potential, because again, nothing is wound up. We didn't wind up a spring, like some sort of rotational spring, like you can pull back on those cars and it winds up a spring, and that's potential elastic, right? Rotational potential elastic actually is what that is. Or if it starts at a height and drops down, it would be losing or gaining, depending on which way it went, gravitational potential energy. So no potential energy involved in this problem. Also notice, this is a rolling problem that takes place on the floor. It's not rolling up and down an incline. So we didn't have to use those generic equations we came up with last class when it comes to rolling down an incline or rolling up an incline. So let's try to categorize rolling into those two types of problems that we're going to be thinking of. Okay, again, one where it's rolling just horizontally and one where it's rolling on some sort of an incline. Eventually we'll see how we can combine those two and see rolling off an incline, projectile motion, and go into that. So again, this is example 3. Example 3. Let's take a look at the next example here. This is example number 4. A uniform solid sphere rolls down an incline. So right off the bat, we see that it's rolling down an incline, rolling down an incline. So we can start thinking about the fact that those formulas that we wrote down a couple slides back are very useful. I'll pause for a moment so you can go back and see them. So it's a solid sphere, it rolls down an incline. The first problem says, what must be the incline angle if the linear acceleration of the center of the sphere is to have a magnitude of 0.1 g? So right off the bat, it seems a bit overwhelming, but let's list what we know. So we know that it's a uniform solid sphere. From our table, a uniform solid sphere is 2/5. And I have the table up in front of me here, so I'm just looking at it as we go through. 2/5 mr squared. We're also told that the linear acceleration is going to be 0.1 g. So we're looking at a fraction of g in this problem. Hang on one second, my brightness is way too high. Okay, there we go. 0.1 g. And then we're looking for the angle. So if we use the formula that we had a moment ago that said A equals negative g sine theta over 1 plus I over mr squared. That's the formula we had written down on that previous page there. So we're going to use this formula to simply solve for theta. Okay, again, A is going to be 0.1 g, and then the I is going to be 2/5 mr squared. That's divided by mr squared. So let's do a bunch of cancellations here. G's on both sides of the equation. Cancels out. Mr squared in the numerator, mr squared in the denominator. Cancel out. Leaving behind 0.1 equals negative sine theta over 1 plus 2/5. And as a result, if we look at this equation, we can see that the only unknown in the problem now is indeed theta. Okay, again, the only unknown here is indeed theta. Now, let's point something out. We'll notice that the negative sign seems to be only on one side of the equation. Remember, when we did this problem, I'm going to pause so you can see, I wrote in earlier, right, this acceleration A that we jotted down, that value, oops, this value A right here should be a negative quantity because it's rolling down the ramp. So this is a negative here, this is a negative here, and then those double negatives right on both sides become positive. And then we can solve for theta. And again, this is part A of the problem. So 1 plus 2/5 is 7/5. Let's multiply 7. So what's going to be 1.4 times 0.1 or 0.14 equals sine theta. And then solve for theta by doing the inverse sine. You'll get 8 degrees. So I want to point out the simple fact here that the derived equation that we came up with really helps a lot when solving problems involving rolling down a ramp. If we have things rolling up a ramp, then we have to consider the fact that the direction is different now. But again, this is for a problem solving rolling down a ramp. The second part, let's use logic to answer the second part. If a frictionless block were to slide down the incline at that angle, right, at that same angle, so the same exact scenario, but now a frictionless block, would the acceleration's magnitude be more, less than, or equal to the one that we just had, and why? Would it be more, less than, or equal to what we just had, and the question becomes why? Chris, why don't you take a stab? I see a hand up. Huh? Yeah, you're on the right track there for sure. The answer is definitely more. We can answer it for two reasons. We could answer it one reason, we could look at it and think, well, we could talk about forces acting on it. And the second way we can think about it, we could look at energy, which is where the rotational inertia is going to play a role that Chris is mentioning there. So I think it's easier to look at it with energy than it is to look at it with forces. So let's say we've got an object at the top here, right? Let's draw ourselves a ramp. And let's say we've got this object rolling down the ramp. And then we've got the exact same ramp, and we've got this block right here sliding down the ramp. For the first scenario, we have to have friction. We know we have to have friction because it's rolling, right? Nothing can roll without some sort of friction. If it were no friction, the circle, right, that little, what do we have, a sphere? That sphere would just slide down the ramp in the exact same way as the box. So without this friction shown right here, these two would have the exact same motion, really. Now, if we think about energy, the type of energy at the top is all potential. And the type of energy when the sphere gets to the bottom is going to be kinetic due to rotation plus kinetic due to linear. Remember, it's going to have 1/2 I omega squared and 1/2 mv squared when it gets down to the bottom there. Whereas the block is not going to be rotating. So its energy at the very end when it gets down here is going to be all kinetic energy due to linear. So think about this logically. If you've got the same amount of starting energy and it all goes into linear energy, it's going to have more linear energy with the block moving. And linear energy is where the 1/2 mv squared comes from, whereas rotational energy is where the 1/2 I omega squared comes from. So if I denote some value, it does not matter what value, let's say it starts with 10 joules of energy in both cases. If at the bottom it still has 10 joules of energy, it means all of it is converted into its linear speed for the block, as opposed to for the one rotating, maybe it's got 2 joules of rotational energy and 8 joules of linear energy. So the question is again asking about what would the acceleration magnitude be, more, less than, or equal to? Well, if the object that is sliding down the ramp without rotating has all linear energy, it means it has more linear velocity at the end. This will have less linear velocity. So this one gained more velocity, so therefore it must have more acceleration. This one gained less velocity, right? 8 versus 10 in energy. So the amount of velocity coming from this 1/2 mv squared is going to be less v. This v value will be a greater v value. And you could try these with numbers, obviously, right? You could plug in values at this point if you want to, but we were not given anything about the mass in this problem. So to go ahead and actually calculate stuff at this point, it's more of a theoretical kind of question. This is the kind of question you could expect on the AP exam after you answer maybe the first or second part of it, where they give you a follow-up that says something like, well, now figure out if this one parameter changed, how would it affect the problem? And that's the kind of answer we're going to be, looking for. And the rationale behind it, you want to think about conservation of energy in this case. The idea of conservation of force, or not conservation of force, of using forces works as well, but it's not as clear. So I personally wouldn't use that explanation for it. Any questions on example 4? Oh, let's keep going. So let's look at this next example. So here we're looking at an example that gives us a graph, also out of the end of your chapter here. So we're looking at, I think, example 6 here. Yeah, example 6. So we're told the following. The figure on the right gives the speed v versus time t for a 0.5 kilogram object of radius 6 centimeters that rolls smoothly down a 30-degree ramp. The scale on the velocity axis is given by Vs equals 4. What is the rotational inertia of the object? What is the rotational inertia? Now, this is the kind of problem that on the AP exam, they would probably give you a bunch of data instead of the graph, or maybe the graph, and then you have to either set up an experiment, remember, or come up with an idea of how to calculate the I value for this object. And you guys, if you recall, you did that actually already in one of the pivot labs. In the pivot labs, your goal was to find like that beta value or the coefficient for the I, which is what we're inherently doing here. We're trying to figure out the rotational inertia, right? Rotational inertia of the object. So this is our goal. What is the I value? That's what we're trying to figure out. But we don't have a lot of information, so let's figure out what we can actually do with this. So we're told that the mass is 0.5 kilograms. The radius of the object is 6 centimeters, or 0.06 meters. The angle that it's sliding down is 30-degree ramp. Let's see, okay, and then we're given a graph. What information can we extract from the graph? What information can we extract from the graph? How can we do that, Chip? Nice. So let's go ahead and figure out the acceleration. And that's the important part here. It's very if we integrated it, you're saying? Yeah, we could get that. I don't think we're going to need it, but we could get that, yeah. It's possible that we could use that if we had something to do with, if we're looking at energies and trying to figure out how much energy was lost or the average force applied and stuff, we could use that there. Yep. So we could go integration or derivative with this one, yep. So the slope, though, of this is going to be, what is this? This is 0.4 at the top. So this is 0.35. Right? Let's see, these are going, that's 0.4, 0.3, 0.2, 0.1, yeah. So that's 0.1, that's 0.2, that's 0.3, so that's 0.35 up here. And that's a 0 there. So, say again? Yes, 3.5, thanks, Chris. So these are all, move the decimal over. So we have a acceleration defined as change in velocity over time. And because this function is linear, we can, as Chip said, just find the slope. Had it not been linear, had it been curved, we'd have to approximate, right, with an actual tangent there. But for these problems, we're looking at constant acceleration when it's rolling down the ramp. So you could expect the graph to be linear here because the acceleration is constant and therefore the slope is constant. If it did something like this, we would have a varying acceleration, and that wouldn't hold true for the formulas that we derived earlier on. Okay, those formulas we looked at earlier on are not for varying accelerations. So the acceleration will be 3.5 minus 0 over 1 minus 0, or simply 3.5 meters per second squared. Let's see. Now, let's point something out. This graph gives us the speed versus time. Speed versus time. So it looks like the speed is getting greater and greater and greater, right? But if we think about the context of the problem, if we look at these problems again, we've been deriving all of our equations with this object rolling, and we've been saying that this is the positive x-axis, and this is the positive y-axis. So this object is going to be rolling down the ramp like that, right, in that general direction. So this is going to be a negative acceleration that we get here. And that's a part that you might just forget about, but it's really important here. Again, this problem does not state that this is velocity versus time. This is speed versus time. So the slope of this gives us the magnitude of the acceleration. This is the magnitude of the acceleration. But because it's rolling down the ramp, as stated, right, it's moving from here down the ramp, we know that it's going to be a negative acceleration. All right, just to point that out before we continue. And what's our goal? Our goal is to find the rotational inertia of the object. So likely, we're going to use that same generic equation again and then solve that for I. So let's go ahead and figure that out now. That generic equation told us that A was equal to the negative of, again, what was this? G sine theta all over 1 plus I over mr squared. I think I wrote that. So when we look at this equation, what we're going to recognize here is that the only unknown now is I. So this just becomes resolving this entire equation for the variable I. M is given, R is given, theta is given, G is given, and A is given. So at this point, it's just solve this equation for I. And if I were doing it algebraically, just to see it happen, I would move things over and switch with the A. I would write it as 1 plus I over mr squared equals negative G sine theta over A. Right, I would switch those two first. Let's see, after that, carry this up here. After that, I would subtract the 1 and then multiply by mr squared. So this is going to be I equals this whole thing minus 1, and then, since mr squared is in the denominator, I would multiply by mr squared on the right side. And that's what the expression for I would end up looking like. Okay, again, moving this over by subtraction, putting that out there, and then multiplying by mr squared to get I by itself. Again, not concerned about the number, but if we want to get a number here, I'll give it to you so you can see it. 7.2 times 10 to the negative 4. And that's kilogram meter squared. All right. Any questions on this one? Do we see how we're going to make some connections now between being given data and have to actually compute or measure or calculate a value that's unknown, such as I? And this is really a lot of the ways that I was originally calculated experimentally and then proved using integration with mr squared. So we did in the very beginning of chapter 10. But I want to keep, or middle of chapter 10, but keep going back and forth between the idea of like, we can prove this experimentally and get an I value instead of actually deriving it. That's again what the second type of problem you could expect for the AP exam will be like. Any questions at all on this one?